Okay, so today we're going to have a look at our new Extension 2 topic, further mathematical induction. So in Extension 1 we have done lots and lots of work on mathematical induction, and Extension 2 we're really just going to be extending upon that knowledge and looking at different types of questions and of course at harder questions. Oh, that has gone funny there. There we go, that's better. So in Extension 1, we always prove results applying to natural numbers. And we always use the inductive step k plus 1. In Extension 2, the base case we test can be greater than 1, so the minimum might be 2 or 3 or 5. And the numbers might jump more than one integer. So instead of proving for all integers, we might prove for all even integers. And importantly, often it's not going to tell you that it's an induction proof. So here we can see in example 1, it doesn't say the word induction anywhere. So prove that n squared plus 2n is multiple of 8 if n is an even positive integer. So instead of testing n is 1, our first initial case is going to be testing n is 2. So 2 squared plus 2 times 2 is 4 plus 4, which is 8. Okay. Now then we would conclude and go, therefore true for n is equal to 2. Our next step is to assume for n is equal to k. So we're going to assume that k squared plus 2k is equal to 8p for some integer p. A positive integer as well. Our next step is not going to be k plus 1, but k plus 2, because if our integer k is even, then the next number that's even is k plus 2. So we're going to look at k plus 2. So we're going to go, okay, well, the left-hand side, we've got k squared plus 2k is equal to our expression, so it's now going to be k plus 2 squared plus 2k plus 2, which if we expand, we're going to get k squared plus 4k plus 4 plus 2k plus 4, which is equal to, we're looking at how can we get k squared plus 2k. So we could say this is k squared, first of all it's plus 6k plus 8, but we could say this is k squared plus 2k, separately plus 4k plus 8. Now this here is equal to 8p, so this is 8p plus 4 k plus 8. Now we could take out a factor of 8 by going, this is 8p plus, now this is k on 2 plus 1. Now we know that k is even, so k on 2 is an integer, so k on 2 is an integer as k is even, so therefore this is equal to 8. We might say m, so which is divisible by 8. So we're done there. So therefore 8m is divisible by 8, so we're proven by induction. Now just because I'm sick of writing today, I'm not going to write the whole end of the proof, so I'm just going to say therefore true by induction. Okay, sigma notation. So I have shown you how to prove using this type of notation, but it's not actually in the Extension 1 course, only in the Extension 2 course. So we're going to have a look at this proof here. So prove for n is greater than 1 that the sum of r is equal to 1 to n of 2r plus 2 to the power of r is equal to nn plus 1 plus 2n plus 1 minus 2. Okay, so the first step would be to prove true for n is 1. So 2 times 1 plus 2 to the power of 1 is equal to 4, and 1 times 1 plus 1 plus 2 squared minus 2, of course, is also 4, So therefore true is n is 1. Our next step is to prove true for n is k. So we're going to go, not prove, but assume true for n is k, that the sum from r is equal to 1 to k of 2r plus 2 to the power of r is equal to k plus 1 excuse me, plus 2k plus 1 minus 2. And our next step is to prove true for n is equal to k plus 1. Okay, so what we're going to do is we're going to look at the left-hand side, and we are going to look at our result to be proven. So we're trying to prove that the sum from r is equal to 1 to k plus 1 of 2r plus 2 to the power of r is equal to k plus 1, k plus 2, plus 2k plus 1 is k plus 2 minus 2. Okay, now we know that the sum from r is equal to 1 to k is equal to 2 to the power of r plus 2r. That's from our assumption. And we're plussing the k plus 1's term. So we've got the sum from r is 1 to k is equal to 2r plus 2 to the power of r, but we want the sum to k plus 1, so we're just going to substitute in the next term, our k plus 1's term. So we're going to substitute in 2 k plus 1 plus 2 to the power of k plus 1 plus k plus 1. So we're substituting in k plus 1 into here. So we've got this sum here. That's our sum from r is 1 to k. And then we're substituting in our k plus 1th term. Now from our assumption, we know what this is equal to. We know that this is equal to this thing here. So that's equal to that, plus 2k plus 1 plus 2 to the power of k plus 1. And that's from our assumption. Now if we simplify that, we're going to get, we can take out a factor of k plus 1 from here. Let's take out a factor of k plus 1 from here, and we're going to get k plus 1, k plus 2, and then we've got plus 2. We've got 2 of these, so 2 times 2 to the k plus 1 minus 2. Now we can use our index laws to say this is 2 to the power of 2k plus 2, so k plus 1 plus k plus 2 plus 2 to the power of k plus 2 minus 2, which is what we're actually after, so we're done. Okay. Our next type of questions are divisibility proofs. Now the only difference from these proofs to the ones in extension 1 is that these questions will have 2 different bases. So we're going to prove that 3 to the power of 2n plus 4 minus 2 to the power of n is divisible by 5 for any positive integer n. Our first step is to prove true for n is 1. So 3 to the power of 2 plus 4, which is 6. 4, 5, 6, minus 2 to the power of 1. Now 3 to the power of 6 is 729, minus 2 is 727. Not quite, what have I done there? 2 to the power of, I think I've written in the question wrong. I think there should be a 2 to the power of 2n, should be there. So this is going to be minus 2 times 1, which is better because we get 725, which is divisible by 5. And then we're going to prove true for n is k, or assume true for n is k. So we're going to assume 3 to the power of 2k plus 4 minus 2 to the power of 2k is equal to 5p for some k and p belonging to the positive integers. And our next step is to assume true for n is k plus 1. So we're going to go 3 to the power of 2 times k plus 1 plus 4, which is 2k plus 6, minus 2 to the power of 2 times k plus 1 is 2k plus 2. Now we want to try and get 2k plus 4 here and a 2k here. So we're going to split this up into 3 squared times by 3 to the 2k plus 6 minus 2 squared times by 2 to the k, because now these are in terms of this assumption up here. Now from the assumption we know that 5p is equal to, or not 5p, we know for example that 3 to the 2k plus 4 is equal to 5p plus 2 to the k. So we can substitute in that into, that should be a 4 there, because I minus the 2 off using our index laws. So we've got 3 squared, which is 9, times by 5p plus 2 to the power of k, minus 4 times 2 to the power of k. If we expand that, 9 times 5 is 45p plus 9 times 2 to the k, minus 4 times 2 to the k. Now 45, of course, is divisible by 5, and 9 times 2 to the k minus 4 times 2 to the k, well, we've got 5 2 to the k's left, which is divisible by 5. So we've got 5, 9p plus 2 to the k, and we're done. Therefore, true by induction. Of course, you need to end your induction properly, but I'm sick of writing, so I'm going to do that there. Alright, now we're going to have a look at inequality proofs by induction. So these are really the ones that separate extension 2 from extension 1. In my opinion, those other 3 questions we've looked at, for an extension 1 student who really knows their stuff, they would be able to easily do those questions, but these ones are where they get a bit more tricky. So prove by induction that 2 to the power of n is greater than n squared. For positive integers, n is greater than 4. Now we're looking at just positive integers. The first positive integer greater than 4 is n is 5. Now 2 to the power of 5 is 32, and 5 squared is 25, and 32 is in fact greater than 25, so we're good. N is k is the next thing we're after. We're going to assume that 2 to the power of k is greater than k squared. Okay, n is k plus 1. Let's required to prove that 2 to the power of k plus 1 is greater than k plus 1 squared. Again, remember, we can't assume that this is true at all. We're requiring to prove it. A lot of people will say required to prove, or like a goal or something. So we know that from the left-hand side, is equal to 2 times 2 to the power of k. But we know that 2 to the power of k is greater than k squared. So if we put a 2 here and a 2 here, that means 2 times 2 to the k is greater than 2k squared. So 2 times 2 to the k down here is greater than 2k squared. So in other words, 2 times 2 to the k is greater than k squared plus k squared, and 2 to the k plus 1 is greater than k squared plus k squared. Now that's actually quite close to what we were required to prove. I've got a 2 to the k plus 1, we've got a greater than, but we've also got we want a k plus 1 squared, and I've got a k squared and a k squared. So that's a bit of a problem because it's not quite what we're after. We know that k plus 1 squared is k squared plus 2k plus 1. So ideally, we want to kill one of these k squareds and replace it with k squared plus 2k plus 1. But we're thinking, how can I do that? So what can I do to replace k squared with 2k plus 1? Well, first of all, we want to go, okay, k squared, well, let's make it equal to 2k plus 1. So we want to get rid of k squared and replace it with 2k plus 1. So let's say, okay, what if they are equal to each other? K squared is equal to 2k plus 1. Well, that's the quadratic k squared minus 2k minus 1. And we're going to try and prove, we want to know it has to be greater than 0 because we want to try and put it in here. So I could say that this is equal to k squared minus 2k plus 1 minus 2. Seems a bit random, but let's just pretend we're completing the square. So this is k minus 1 squared minus 2. Now this is greater than 0 because k is greater than 4. So this expression has to be greater than 0. So therefore, k squared minus 2k minus 1 is greater than 0 for k being greater than 4. That's good for us because we've just said, okay, k squared minus 2k minus 1 is greater than 0, which means k squared is greater than 2k plus 1. That's very good because that also tells us that 2k plus 1 is less than k squared. Right. So what we were trying to do initially, if I copy this here and put it down here, what we were trying to do initially is we were trying to replace this with 2k plus 1. But I can't just randomly replace things in an inequality without it really affecting the inequality sign. But in this case, it does end up working out quite well, because 2 to the power of k plus 1 is greater than this whole expression. But if I replace k squared with 2 to the k plus 1, well, this inequality is still true because 2 to the k plus 1 is less than k squared. So say if k squared was 5 and I replace it with 2k plus 1, which might be 4, well then it's still, this expression is going to be less than what it originally was, which means it's still greater than this expression. So if 2k plus 1 is less than k squared, then if I replace it, k squared with 2k plus 1, this whole expression here has gotten smaller because this is less than that. And if it's gotten smaller, this still has to be greater than it. So therefore 2 to the power of k plus 1 is greater if we factorize it k plus 1 squared, which is what we're required to prove, QED. Awesome. Thank you.